is flying by on this busy, crowded planet. As life changes and evolves from second to second. And yet the arc of human lifespan is getting longer. 65 years is the global average, way up from just 20 in the Stone Age. Modern science, however, provides a humbling perspective. Our lives, indeed the lifespan of the human species, is just a blip compared to the age of the universe, at 13.7 billion years and counting. It now seems that our entire universe is living on borrowed time, and that even it may be just a blip within the grand sweep of deep time. Scholars debate whether time is a property of the universe or a human invention. What's certain is that we use the ticking of all kinds of clocks, from the decay of radioactive elements to the oscillation of light beams, to chart and measure a changing universe, to understand how it works and what drives it. Our own major reference for the passage of time is the 24-hour day, the time it takes the Earth to rotate once. Well, it's actually 23 hours, 56 minutes, and 4.1 seconds, approximately, if you're judging by the stars, not the sun. Earth acquired its spin during its birth, from the bombardment of rocks and dust that formed it. But it's gradually losing that rotation to drag from the moon's gravity. That's why, in the time of the dinosaurs, a year was 370 days. And why we have to add a leap second to our clocks about every 18 months. In a few 100 million years, we'll gain a whole hour. The day-night cycle is so reliable that it has come to regulate our internal chemistry. The fading rays of the sun, picked up by the retinas in our eyes, set our so-called circadian rhythms in motion. That's when our brains begin to secrete melatonin, a hormone that tells our bodies to get ready for sleep. Long ago, this may have been an adaptation to keep us quiet and clear of nighttime predators. Finally, in the light of morning, the flow of melatonin stops. Our blood pressure spikes, body temperature and heart rate rise as we move out into the world. Over the days and years, we march to the beat of our biology. But with our minds, we have learned to follow time's trail out to longer and longer intervals. Philosophers have wondered, does time move like an arrow, with all the phenomena in nature pushing toward an inevitable end? Or perhaps it moves in cycles that endlessly repeat, and even perhaps restore what was there. We know from precise measurements that the Earth goes around the Sun once every 365.256366 days. As the Earth orbits, with each hemisphere tilting toward and away from its parent star, the seasons bring on cycles of life. Birth and reproduction, decay, and death. Only about 1/billionth of the Sun's actual energy hits the Earth, and much of that gets absorbed by dust and water vapor in the upper atmosphere. What does make it down to the surface sets many planetary cycles in motion. You can see it in the annual melting and refreezing of ice at the poles, the ebb and flow of heat in the tropical oceans, the seasonal cycles of chlorophyll production in plants on land and at sea, and in the biosphere at large. These cycles are embedded in still longer Earth cycles. Ocean currents, for example, are thought to make complete cycles ranging from 4 to around 16 centuries. Moving out in time as the Earth rotates on its axis, it completes a series of interlocking wobbles called Milankovitch cycles every 23 to 41,000 years. They have been blamed for the onset of ice ages about every 100,000 years. Then there's the carbon cycle. It begins with rainfall over the oceans and coastal waves that pull carbon dioxide into the sea. There it's captured by ocean plants, including tiny organisms called plankton. They are eaten by fish and other creatures, and the carbon is passed on up the food chain. Eventually, when plants and animals die or expel waste, the carbon falls to the ocean bottom, where it's impounded in layers of sediment. Without people, it takes a volcanic explosion or a dramatic lowering of sea levels to send the carbon back into the air, often after millions of years. The idea that Earth and life changes on deep timescales emerged in revolutions of thought associated with Copernicus and Darwin. But the processes that shape a planet like ours play only the smallest of roles in the evolution of the cosmos. So to glimpse time's broadest arcs, we must look to the universe beyond. The reigning theory is that it all began in a sudden expansion of space, the Big Bang. This was the time of the very tiny. The first microseconds set in motion the primordial era. Atoms formed within a hot soup of subatomic particles. The universe cooled as it ballooned outward, growing dim and falling into what's known as the cosmic dark ages. But gravity was always at work, particles pulling on one another. And after several 100 million years, considerable clumps of matter had drawn together. These isolated pockets of gas became dense enough to heat up and ignite. So began the era of stars. In this glorious age, the universe planted the rich cosmic landscapes we see in our telescopes, where hundreds of billions of stars light up galaxies all across the universe. The arc of this great era of stars is defined by the life cycles of those stars, which vary according to their sizes. Stars shine because gravity crushes matter into their cores. The energy released pushes outward and balances the inward force of gravity. This battle between energy and gravity is still raging in stars all around the universe. But in large stars, about 10 million years after their birth, gravity gains the edge and tips the balance. When the core of such a star crosses a critical mass threshold, it collapses in on itself. The energy released causes the star to explode in a blast of light and debris that's visible across the cosmos. In the wake of this supernova, shockwaves can cause nearby clouds of dust and gas to collapse and catch fire, to form a generation of smaller stars like our Sun. But when Sun-like stars go, their end will be more of a whimper than a bang, as shown in this gallery of dying stars captured by the Hubble Space Telescope. As their cores get heavier and heavier, over billions of years' time, fierce winds will begin to push on their outer layers, causing them to blossom out in spectacular displays. That's just what happened about 12,000 years ago to the star that's become the famed Helix Nebula. Today, we see the dying star's outer layers form a vast glowing ring. On the inside of the ring, spokes of more dense gas are being exposed by its winds. The star itself is now a dim, cooling remnant called a white dwarf. It's the size of the Earth, but about 3 million times more dense. This is likely what's in store for our Sun. A civilization distant in time may scan the Sun for planets, but they won't see Earth. Our home planet's end will have begun long before that, as rising solar luminosity gradually blasts away its atmosphere, rendering it uninhabitable. Surface water will disappear, evaporated by all that heat and stripped off by solar winds. Finally, as the Sun